And as I mentioned before, I'm going to be recording it. So I'm going to be writing on the tablet here. So I'll go on the screen and hopefully it'll all work and all that good stuff. All right. So chapter 2 here, we're going to start with, we're going to talk about measurements in this chapter. We're going to talk about significant figures, how to take measurements. We'll also talk about conversions and doing really what's referred to as dimensional analysis, which is the way they really want you to sort of do all chemistry calculations. And as we talked about the other day, they're really trying to emphasize in this class, to set you up for hopefully success as you continue on in 1A and 1B. So we'll talk about how to do sort of dimensional analysis calculations and set it up. And I think we'll finish up the chapter talking about density and all that good stuff here. So obviously the very first thing that's really important when we do take a measurement is units. So if we have just a number, for example, if somebody just recorded 100, really that number has kind of no meaning. We don't really know what that is, what that's referring to. If I had $100, that's very different than if I had 100 pennies. Also very different than it's like 100 degrees outside, which it seems to always be lately. But, so those are all different things. So always when we take measurements, we should always include a number and some type of unit. So maybe it is pennies here. And we should always have a number and a unit. So always those two things should always be included in everything that you record. You should never really have a number by itself. When we talk about sort of units, there really is sort of two widely used sort of types of units that we come across. They're sort of used a lot here in the US, and then pretty much everybody else in the world uses the metric system. So obviously that can cause a lot of problems and a lot of situations where, we're using different units, and depending on sort of your location, as the world got smaller-ish and we kind of interact with everybody in different places, around 1960, they decided perhaps we should have sort of a standardized system of units. And that is what is sometimes referred to as the SI units. And that's like the International System of Units. So they actually had a whole conference on that. Seems like a fun time in 1960 to talk about units, I suppose. And they came out with basically this SI units. So a lot of times in chemistry, we'll see like the SI unit is this, or the SI unit for mass is, kilograms, whatever it may be. Really, the SI unit is really basically a form of the metric system. So it's really more based off of the metric system than it is sort of the English system here. So here's a table of some of the SI units that we see for different types of quantity. And it's important in this class and other classes that you take that you do understand when you look at a unit, what it actually is sort of referring to. So the SI unit for mass is the kilogram. Although I will say in most cases, when we're doing some type of mass measurement like we are doing today in lab, we use grams a lot. Length, the SI unit is meters. Time, the SI unit is seconds. And a unit of temperature, which you may not be familiar with yet, but if you continue to take chemistry, you will be very, very familiar with this guy. That is the Kelvin, unit of temperature. And I would say pretty much every single chemistry formula, except for a few, but almost 99% of them, if you have to use temperature, it has to be in that unit. It has to be in Kelvin. And we're going to talk about how to convert to that in just a bit here. So these are the standard sort of units that we see. SI units for when we're measuring mass, we're measuring length, we're measuring time, and when we're measuring temperature. It's important to understand, the differences between units and what they represent. When we have something like liters, for example, that is actually a unit of volume. And our milliliters, which is a very common unit of volume that we come across. And I can't tell you how many times people say like, hey, the mass was like 20 milliliters. And so you really want to make sure that you understand the relationship between the unit you're looking at and really what it is referring to, what it is really measuring. So let's talk a little bit about some common units of length, volume, and mass that we come across. 1 meter is about 39.37 inches. These are some common units of length that we do come across a lot, and that is the centimeter and the kilometer. Again, I would say centimeter, kilometer are very common units that we do come across. 1 centimeter is 0.01 meters, or there is 100 centimeters in 1 meter. So these are two sort of relationships that you should know, and we do come across centimeters and meters type conversions a lot. 1 decimeter is 0.1 meters. 1 kilometer is 1,000 meters. That's another one that does pop up a lot. So that is definitely probably something you should know. So I would say, you should know those guys. This is basically the version written in scientific notation. 1 times 10 to the 3 is 1,000. 1 times 10 to the minus 1 there is 0.1 decimeters. So anything really involving meters, that is again a unit of length type of measurement. Here are some prefixes, which you should be familiar with as well. And we have mega, kilo, deci, centi, milli, micro, and nano. I would say for sure in this class, kilo comes up a lot. Centi, as we just talked about, milli. I will say in 1A, you'll probably come across these two here a lot. Nano and micro will pop up a lot. These are the meanings here. So this is again, how many of the base unit there is in 1 prefix unit. And what that means is, as we saw on the previous page, if you had 1 centimeter, that would be 0.01 meters. So meters here is the base unit on both of them. Centimeters is the prefix unit. We get the other conversion we saw by basically dividing the 0.01 to both sides, and that gives us that there are 100 centimeters in 1 meter. So that is how we get that, by dividing this to the other side. Now, you should know those. Definitely should know kilo, centi, milli. You probably should know, I would say, nano as well. That might pop up. These are the power to 10 notations of that. And I'm going to show you how to use those, even though they don't want us to, I suppose, but I'm going to show you anyways. So a lot of times when you look up or you find sort of a prefix table, you'll see sort of these guys listed. And it is very, very common that people pull off that information and always use it backwards. So what we see here is how much there is, once again, in the base unit to 1 prefix unit. So for example, 1 centimeter would equal 10 to the minus 2 meters, just like 1 kilometer would equal 10 to the 3 meters. So it's very common. People always want to write something like 10 to the 3 kilometers is 1 meter. So they always want to go backwards on that. So what you see there is how much there is of the base unit to 1 of the prefix unit. By the way, 10 to the 3 or 10 to the minus 2 is 1 times 10 to the minus 2 in scientific notation. We'll talk about that in a bit as well, how to punch that in, or 1 times 10 to the 3. So, you know, you definitely can use those, and we can use them as conversion factors. But again, it's a very, very common mistake that people make. The other thing that I guess sometimes people don't also tie together is it really doesn't matter what the base unit is. The prefix is the same no matter what the base unit is. So what I mean by that is 1 kilogram would be 10 to the 3 grams. So it's the exact same relationship, just the base unit change. You know, if you had 1 kiloliter, that would be 10 to the 3 liters. So again, it doesn't really matter the base unit, the prefix is the same. You can apply it to any sort of base unit you want that represent length, volume, whatever it may be. Any questions on that there? Okay. So here's a ruler that shows the difference between sort of the English and metric system. And by the way, this is a ruler. Up on top is inches. Big numbers on the bottom are centimeters. Little numbers on the bottom are millimeters. Yeah, so the little ticks are millimeters. There are 10 millimeters in 1 centimeter. In 1 inch, there's 2.54 centimeters. So it's good to know how to use a ruler, I suppose. So big numbers up here, inches. Numbers up here are centimeters. Little numbers, millimeters, as you read through them. 1 inch is exactly 2.54 centimeters. Star that. That's like the conversion everybody wants you to know. So you do need to know that one. That 1 inch is exactly 2.54 centimeters. So let's talk a little bit about some of the units that we see associated with volume. And again, there'll be some common units that we see. Volume is basically the amount of three-dimensional space that is occupied by a substance. Volume is length cubed. The SI unit is meters cubed. We really don't use meters cubed all that much, but there are some relationships that we do use a lot and you need to know. And it's really these bottom ones down here. So you do need to know those two for sure. 1 cubic centimeter is equal to 1 milliliter. And there are 1,000 milliliters in a liter. That is like something you come across daily when you're doing calculations a lot, both for these guys. Actually, 1 liter is not a meter cubed, but it's actually a decimeter cubed is a liter. How do we get to something like a cubic centimeter? We could calculate the volume of an object by taking like the length times the width times the height. And if we measure each of those length measurements in centimeters times centimeters times centimeters gives us a cubic centimeter, which is a volume. So each of those individual measurements of centimeters, centimeters, and centimeters, they're all length measurements. When we multiply them together in this application here, we actually will get the volume of it, which is a cubic centimeter. And once again, 1 cubic centimeter is equal to 1 milliliter. And sometimes a cubic centimeter is represented also as a cc. You hear that a lot in medical shows. Give the guy 5 cc's before he dies, right? It's basically 5 milliliters or whatever they're pumping into him. So I would say here in the US, we don't usually use it too much in chemistry, the cc, but it is the same thing as a cubic centimeter when we look at it. Any questions on that there? Now let's talk a little bit about mass. Mass is the quantity of matter that is present in an object. And there really is a difference between mass and weight, as we'll probably see, I think. But mass is basically independent of gravity. Weight is dependent on gravity, the force of gravity. So you would weigh something here on Earth and you would weigh about 1/6 this weight if you were on the moon, because the gravity is different. But your mass would be the same. So you should get into a habit when you weigh something and you talk about sort of the value that you get when you weigh an object, you should really refer to it as the mass of the object. So we don't really refer to it as the weight of the object. We refer to it as the mass of the object. Matter is basically anything that occupies space and takes up some mass and area. The fundamental unit, as I mentioned before, mass is kilograms. Although, as I mentioned, it is really grams that we use a lot. And that's an important relationship. In 1 kilogram, there are 1,000 grams. So that is something you should know. And again, that's the same as this kilometer-meter relationship we just saw basically a few slides back. It's the same relationship. The other sort of common mass unit that we come across a lot is milligrams. And it's really the sort of milli prefix, if you will. And just like we just saw with our volume, that there are 1,000 milliliters in 1 liter for our volume, there would be 1,000 milligrams in 1 gram. So the mass relationship there, again, these relationships, as I mentioned, are basically the same. It doesn't matter the base unit that you come across. So again, as I were going through these, and I'm saying you should kind of know them, as we talked about before, there are a lot of conversions that they do want you to sort of know by heart here. Any questions on that? So as I mentioned a second ago, there is a difference between the two words of weight and mass. And as I mentioned, it is really weight that is dependent on the force of gravity. And again, mass is sort of independent. It's sometimes confused by people because what we're looking at, by the way, and we'll also use obviously today in lab, is something like this. That's what is referred to as a balance. That is I guess a fancy word for a scale. Right? That's an electronical balance there. And again, the process that we obviously go by to get the mass of an object is a process known as weighing. So that's why a lot of people, I'm sure, calls it weight. But again, here in chemistry, you should refer to it as the mass of the object. So earlier we saw that their SI unit for temperature is the Kelvin, and there really are 3 different temperature scales that we come across. There is degrees Fahrenheit, degrees Celsius, and then there is Kelvin. The first major difference is how we refer to each of those. It is degrees Fahrenheit, degrees Celsius. We do not use the degree little symbol or say degrees with Kelvin. It's just like 400 Kelvin is how we refer to it. So it's not 400 degrees Kelvin. It would just be 400 Kelvin. On the Fahrenheit scale, which is what we use for like our temperature and all that good stuff, water boils at 212 degrees and it freezes at 32 degrees Fahrenheit. That's a scale we use a lot. On the Celsius scale, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. And again, the third temperature scale, which is the one we use a lot here in chemistry, the Kelvin scale, water boils at 373 Kelvin and freezes at 273 Kelvin. I would say probably outside of chapter 2. Yeah, probably won't see too much of Fahrenheit, but we definitely get a lot of temperature readings recorded in Celsius. And a lot of what we do in chemistry is go from Celsius to Kelvin. So that conversion between Celsius to Kelvin is one that we do a lot. Again, outside of chapter 2, might not see a lot of Fahrenheit. So let us actually talk about how we do the conversions between them. And here's the 3 different temperature scales. And really the reason we do the conversions and why we do the conversions is really the difference between freezing and boiling points on the different scales. So on Celsius and Kelvin, there's about 100 units of difference between boiling and freezing. And on the Fahrenheit, there's about 180 units of degree difference between where boiling and freezing of water occurs. So that gives us really the 3 ways that we convert temperature, and they're in boxes. So again, you should know how to do these by heart. They will not be provided for you. We'll talk about converting Kelvin to Celsius, which is pretty much the main one that we do. And to do that, it's not too bad. You just add 273 to the temperature in Celsius. So you take the temperature in Celsius, add a 273. The correct proper number is 273.15. I don't know very many people that kind of keep the 0.15 part of it. Most people get rounded off anyways. So I'm good with 273. But if you see somebody say 273.15, that is actually the true number that you're supposed to use. But very few people use the 0.15 part of it. And that is 100% conversion that you'll do a lot in chemistry, is take the Celsius, add 273, and you get the temperature in Kelvin. Obviously, it means if you want to go backwards and you want the temperature in Celsius, you take the temperature in Kelvin and minus 273 to do that. So take the temperature in Kelvin minus that 273 to go backwards to do it. Converting between Fahrenheit and Celsius, the temperature in Fahrenheit is 1.8 times the temperature in Celsius plus a 32. And if we wanted the Celsius and we have the Fahrenheit, it is the temperature in Fahrenheit minus 32 divided by 1.8. That 1.8 is equivalent to your 9/5. Oops. If you take 9/5, that is 1.8. I had a moment there. So you might have learned the fraction version of it. It's the same conversion as you go through there. Some people use 1.80. Some people use 1.8. Some people use 9/5 on these conversions. So the general rule, when we're sort of doing nothing more than a temperature conversion, is we basically take the original number and we convert the temperature scale and we make our converted value look like the original value. So what that means is if our original temperature value was a whole number, when we do the conversion, we keep it as a whole number. If our original temperature scale, our value went to the first decimal place, when we convert it, we would take it to the first decimal place as well. So temperature conversion is one place where it doesn't necessarily follow strict significant figure rules. And it's really because of that variation of, 1.8, 1.80, 9/5 and that nature. So the general rule is whatever the original temperature number looked like, when you convert it, it should look the same. It should go to the same number of places. Any questions on that there? All right. So take a second or two here and do the conversion for each of these. Okay, let's take a look and kind of see how we're doing. So we'll start with the first one. we basically have 28.5 degrees Celsius. We want to convert it to Kelvin. So that is our temperature in Kelvin is equal to our temperature in Celsius plus a 273. That means we got 28.5 plus 273, and that is going to get us 301.5 Kelvin. So once again, no degree Kelvin on that. It's just Kelvin. The original value went to 1 decimal place, so we took the converted value to 1 decimal place. Any questions on that? Next one, we have basically Celsius, and we want to convert to Fahrenheit. So our temperature in Fahrenheit is equal to 1.8 temperature in Celsius plus a 32. That gives us 1.8 times 41 plus a 32. And gets us 105.8 degrees Fahrenheit. On this one, though, when we look at our original number, it actually was a whole number. So we would want to then round this guy to 106 degrees Fahrenheit. Again, making it look like our original number. So our original number, whole number. Here we would round it also to a whole number. Any questions on that there? Lastly, we're going from Fahrenheit to Celsius. So our temperature in Celsius is equal to our temperature in Fahrenheit minus 32 divided by 1.8. That gives us 160 minus 32 divided by 1.8. Gives us like 71.1111 degrees Celsius. Once again, looking at our original number there, it's a whole number, so we would want to take that to 71 degrees Celsius. Any questions on any of those there? Okay, so again, that is just sort of a special rule for how we do conversions, strictly temperature to temperature conversions. We just make it look like the original number. And again, you do need to know how to do these conversions. And the one that really should stick with you is the Celsius to Kelvin conversion is the one you do a lot in chemistry. All right. So what type of measurement is each of these? 523 Kelvin would be a temperature, yes. Kelvin is a unit of temp. 25.36 liters would be a, what would it be? It would be a volume, yeah. 15 meters would be a length. And kilograms would be a unit of mass. So again, it's really important to understand the relationship between the unit you're looking at and what it basically represents in terms of a quantity of a measurement. So I don't want to hear anybody say my mass was 40 meters, right? Or anything like that. Or 40 milliliters or something like that. All right, that was that one, I think. So let's talk a little bit about a couple of types of sort of observations that we make. Qualitative is basically consisting of general observations about a system. You know, it turned purple, there was a solid that formed, it started to bubble, those type of sort of observations. Quantitative is basically measurements. So quantitative comprised of values, numbers, and measurements. So whenever you take any type of measurement, you are doing quantitative work. When you're taking observations, like I mentioned before, you know, colors, what you observe happening, nothing a direct sort of measurement of, but just really observing the system as it's changing. Those are, again, more qualitative evaluations that you're making. If you go on to 1B, you do a bunch of what are referred to as qualitative analysis experiments. And pretty much there's no measurements other than you observe what happens. It makes a solid, it disappears. These are things that you do in those type of experiments. Most of the experiments that we do in our lab here are really quantitative measurements. We take values and stuff like that. Sometimes when we are dealing with really large numbers or really small numbers, there's a lot of zeros involved, which means if we try to keep all those zeros on those numbers and we kind of move through calculations and stuff like that, there's a fairly good chance you're going to probably screw up and miss a zero somewhere along the way. So we do use the process of writing numbers, which is referred to as scientific notation, to handle really large values, really small values as well. And scientific notation has a general form, as you can see there, of n times 10 to the n. This first guy here is a number between 1 and 10. It has to be a number between 1 and 10. It cannot be 10, 20, 100. Can't be point something. It needs to be a number between 1 and 10. The top little n there is also a whole number that can be either positive or negative, depending on sort of which way you need to move the decimal place to get yourself a number between 1 and 10. So whichever way you need to move it to do that determines whether or not that's going to be positive or negative. If I had 1, 2, 5, 6, I would take the decimal point, which would be assumed here, and go 1 place, 2 places to the left. And that would give me 1.256 times 10 to the 3. And that would be proper scientific notation. If I had a smaller number like 0.00111, I would take the decimal place and go 1, 2, and 3 places to the right. That gives me 1.11 times 10 to the minus 3. As you can see, if you move the decimal point to the left, you have a positive exponent. If you move it to the right, you have a negative exponent. Easier way to remember it as well is if it's a large number, it's a positive exponent. If it's a small number, it should be a negative exponent. And you do need a key-o to get a number between 1 and 10. So for example here, if we looked at these numbers and we converted them into scientific notation, and none of them are negative, that's just PowerPoint, so none of them are actually negative. But here we have 568.762, and we want to convert it into scientific notation. We would move the decimal place 1 and 2 places over to do so. And we would end up with 5.68762 times 10 to the 2. For the second one, we would need to go this way. 1, 2, 3, 4, 5, and 6 places. That's a small number, so that gives us 7.72 times 10 to the minus 6. And lastly, here we would go 4 places, and that would get us 1.25 times 10 to the 4. You may be wondering why we kept maybe some of the numbers, why we got rid of some of the numbers. It will become more clear when we talk about significant figures, but that is really the reason why. This number up here actually has 6 significant figures. And when you write a number in scientific notation, all the numbers before the times 10 part are significant. Should never lose significant figures as you go from decimal to scientific notation and back and forth. Same thing here, this actually has 3 significant figures, which is why we only have 3 significant figures represented here. We'll talk why this guy only has 3 significant figures, which is why we have 3 significant figures represented here. So We should never lose significant figures when we gonna do the conversion. And then obviously here, going one place to the right there gives us 1.35 times 10 to the minus 1. All right, so once you do this one, write this in scientific notation. At this point, the 4, the 2, and the 5 are the only significant figures there. All right, let's take a look. So on the first one, we would assume here, so 1, 2, 3, 4, and 5 places gives us 4.25 times 10 to the 5th, if I counted right. Over here, decimal 1 place, 2 places, 3 places, 4 places, 5 places, 6 places, 7 places, I think. Gives us 8 times 10 to the 7 grams, and it would be negative since it's small. And meters on the units. Any questions on either of those? All right. More importantly, in terms of scientific notation, and to answer maybe some questions, do you need to write every single number in scientific notation? The answer is no, you don't really need to do that. If you want to, you can. There are sometimes the only way to sort of give the answers a correct number of significant figures is to write it in scientific notation. But more importantly is how to actually punch these into your calculator. So let's take a moment here to make sure everybody knows how to do that. On your calculator, you should have actually a exponent button. It is either an EE button, it is either an EXP button, or if you have some of the fancy new calculator, might have a times 10 to the N button. And usually if you have that button, you also have like a little wheel on your calculator. It looks something like that. So if you do have that, we'll talk about you in a second. If you have one of these two guys, let's talk about how you properly use these buttons. If you had something like 6.25 times 10 to the minus 4, and you wanted to punch that into your calculator correctly, you would type in 6.25. You would then hit your exponent button. And in most cases, it will go 6.25. It will pop an E, or it might go 6.25, maybe pop up some zeros up on top, or times 10 to a couple of zeros up on top, something like that. When you hit the EE button or the EXP button, it represents this part of the number, the times 10 part, which means you don't need to hit the multiplication button. You don't need to hit the second log button. If you're doing any of those things, the caret button, you're going to be wrong. Yeah, so this is the button that you should use. What's left is actually just the -4 part of the number. So you also on your calculator have a negative button. Usually looks either like this or like that, not your subtract button. So some button like that is what you want. So you would hit your negative button there. And 4, that would give you -4. We'll turn this into like a -4 at that point. And that is the proper way to punch something in your calculator in scientific notation. So you absolutely should not use the multiplication button unless you're multiplying that number by a number, or the log button, the inverse log button, the caret, any other crazy thing people like to do. Now, if you have this button or those two buttons, you pretty much have to do the same thing, except that you have to really put parentheses around every single number because of the way the calculator is programmed. So you need to open up with a parentheses. You need to hit the 6.25 and then that button. That will give you a parentheses. The 6.25 will probably go times 10, and you'll have a little cursor that's blinking up on top. At that point, you could do your negative button. And it will then turn it into 6.25 times 10 to the -4 with your cursor button next to the 4 now, and it's still up on top. That is where this little circle comes into play. You want to hit the right-hand side of the circle. That will bring your cursor back down, and then you can close the parentheses, and you'll end up with this. So a little few more steps along the way if you have that button, but it does work. You just got to pretty much parenthesis out every number. Otherwise, most of the time those calculators will break up the number and do the multiplication part wrong. It'll kind of multiply wrong and it'll be off. Any questions on that? If you're not sure where your exponent button is, you should come see me. We'll find it together if you need. Why don't we try one just to make sure? Let's do 1.25 times 10 to the minus 4. We'll divide it by 2.5 times 10 to the 12. See what you come up with. Okay, so if we're going to punch this in, I would go 1.25. I would hit my exponent button. I would hit my negative button, and I would hit 4. I would hit my divide button, 2.5. Exponent button. In this case, it's a positive exponent, so I don't need the negative button, obviously. And I would do 12 and the equals button. So if we do that, looks like it's going to be 5 times 10 to the minus 17. Now on your calculator, it may give you just 5 times 10 to the minus 17. Proper sig figs would be 5.0. And again, we'll talk about that in just a second. Also, don't forget to include the times 10 to the minus 17. Part of it, sometimes people just write the first number they see without the exponent part on the answer. If you find yourself punching these things in wrong, typically what will happen in your answer is this part will be okay, but this part will be off by a little bit. And that usually is an indication that you did not punch it in correctly. When you give an answer in scientific notation, that is how you should write it. 5.0 times 10 to the minus 17. You should not write 5.0 e minus 17. So when you're given the answer, that is the proper way to sort of write it. Any questions on how to punch that in there? That I think is almost more important than knowing how to actually write it in scientific notation. Okay. So the next thing we're going to talk about is actually uncertainty in measurements. And pretty much whenever you take a measurement, there's always some degree of uncertainty in that measurement. There's some type of estimation that has to occur. And the amount of the estimation really is based on the equipment that you use. So for example, let's see here. Make this a lopsided ruler here. All right, so let's say we have a ruler here and we want to measure this little arrow right about here. When we look at this ruler, we have 1 centimeter and then we have 2 centimeters. There are usually big markings or larger markings on it. And in this particular case, the big markings represent 1 centimeter. When we look at the markings between the large markings, we can count up how many we have. In this case, we always start to the right of the next big marking. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, basically coming all the way across there. So we have 10 of the little markings. And if there are 10 markings between 1 centimeter, each marking represents how much? How much would each one represent? It would be 0.1. Yeah, I take 1 divided by 10. Yes, then you would end up with 0.1. So this would represent 0.1 centimeters. This would be 1.1. If I get my hand out of the way there, try that again. 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, and so on. So when we look at it and we take a measurement, there really should be numbers that everybody agrees upon. No matter who takes a peek at that, everybody should agree upon that at least 1.4, and we would record that as 1.4. But obviously, when we look at it, it is not exactly on 1.4, not really exactly on 1.5. And our ruler is not exactly straight, but it's all right. But we're somewhere in this area here. And that's really where the estimate will come into play. I may look at it and go, I think it's just a hair over half. I think it's something like 6, maybe. And I would record centimeters. Somebody else may look at it and go, I think it's kind of half. Maybe it's like 5. Maybe somebody with their eyes sort of closed would look just like a little bit more the other way. Maybe it's 3 or something like that. And that's really where the uncertainty comes into play. When we record a measurement, we should always record all of the certain numbers plus the first uncertain number. So you should always record all of the certain numbers plus the first uncertain number. And really what that is, when you do that and you do both of those things, that is really the significant figures. So this measurement of 1.46 would have how many significant figures? It would have 3 significant figures. Yeah. Oh, yeah, it has 3 significant figures. Now, typically speaking, we could take the measurement to one more place to the right of the smallest marking is typically what you could do. You could sometimes calculate what some people calculate the precision of this instrument by taking the smallest markings and dividing it by 2. So for example, in this case, the smallest marking is 0.1. If we divide it by 2, we get 0.05. So sometimes people will record this 1.46 centimeters plus or minus 0.05 to indicate how far you can take the actual reading to. I'm not a tremendous fan of that, but some people will do that. You don't have to do that for me, but others, maybe as you go to 1A, might want you to do it that way. But you definitely should record this as 1.46 centimeters, which would have 3 significant figures. Now, it does depend on the piece of equipment that you're using. So let's say we had something like let's say we had a graduated cylinder here-ish. Not good quality control at the factory, but maybe why I failed art 4 times, but that's all right. So this is a very badly drawn graduated cylinder. And when we do put liquids in glass containers like a graduated cylinder, we typically will see this kind of curvature. I'm going to draw an exaggerated version of it. Curvature of the liquid when we put it in there. And that is because the attractive forces between the liquid and the walls of the container are actually stronger than the liquid's forces to itself. So the outside kind of crawls up the wall of the container. This is what is known as a meniscus. And you should always read at the bottom of the meniscus. You should always take the reading at the bottom of the meniscus because that's really where the liquid is. The outside is just kind of faked out for it crawling up the walls. So if we looked at this, our big markings would represent 10 milliliters, right? So we have a 10 marking and a 20 marking. Once again, if we count up the markings, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings as we go from 10 to 20. That means each of the small markings is how much in this case? There's 10 markings, 1 milliliter, right? Would be how much each of the small markings represent. That means when we look at our measurement here and we read from the bottom of the meniscus, it is at least 11, 12, 13, 14. It is at least 15, as 16 is above it. So we would record 15. It's not exactly at 15. It's not exactly at 16 in my bad drawing here. So again, there's some type of estimate that we have to make. And in this particular case, maybe you do think it's about halfway there, and you record 15.5 milliliters. Our certain numbers would be the 1 and the 5. And in this case, this would be our first uncertain number. How many significant figures would that number have? It would have 3 as well. Again, so this number would have 3 significant figures. But the precision is a little bit different in this case. Again, if we take the 1 and we divide it by 2, 1 is the smallest marking, dividing it by 2 gets us a precision of plus or minus 0.5 centimeters to the first decimal place. On the ruler, we were able to obviously go to the second decimal place based on the precision of that equipment. Any questions on that? Now, it's not 100% of the time always one more place to the right. So let's say we had our little different graduated cylinder, I suppose. We're getting worse at the factory here. So that is big markings here is still going to be 10 milliliters. But in this case, there is 1 marking, 2 markings, 3 markings, 4 markings, and 5 markings. And we'll put our guy right about there. Now, if there's only 5 marks between those 10 milliliters, each mark represents how much? Yeah, each mark represents 2 milliliters, right? Which means this would be 12, 14, 16, 18. Now, when we take our reading, we're somewhere here, right? That's actually between 16 and 18. What comes between 16 and 18? 17 is the best you could do on this piece of equipment. You would record 17 milliliters. In this case, there's not enough room between those two to figure out where like 16 starts and ends and 17 begins and 18 stops and all that kind of stuff. This would have how many significant figures in this case? It would actually have only 2 sig figs. The uncertain number would be which number? It would be the 7, right? It's basically saying, hey, it could be like 18, could be like 16, is somewhere in that ballpark. Our certain number would be there. And we see that if we did our precision little calculation, 2 divided by 2 is basically 1 milliliter, right? Plus or minus 1 milliliter is the best we could kind of do on this particular equipment. Any questions on that? Now, another common mistake that a lot of people make is, we'll come back to this guy. And we'll put another line up there. So on this one, let's just say we had a line that was like dead on, like the 1.4 marking. What should I record in this case? 1. I'll just go here somewhere, right? 1.40 centimeters, 1.4 centimeters. Is there a difference in those two recordings? Yeah. It is a difference in the significant figures, right? The first one that we recorded would have how many significant figures? It would have 3 significant figures, which means the uncertain digit or the estimated digit would be which one? It would be the 0, right? So the estimated digit or the uncertain digit is always the last significant figure that there is. Notice I said the last significant figure, not necessarily the number that's written. So it's the last significant figure. This guy at 1.4 would have 2 significant figures, right? Estimated digit would be in this case 4 there. That means if we look at that one first, what we're really kind of saying is, I think the measurement's like 1.4, but maybe it's 1.5, maybe it's 1.3. That's a pretty big jump. If we come back here, you can see it's like nowhere near either of those numbers, right? It's pretty far away from each of those. But by recording it actually correctly like this, what we're saying is, I think it's 1.4 centimeters, but maybe it's like 1.41, maybe it's 1.39, which if we come back and look at it, that does seem pretty reasonable. So it's really important that if you hit something right on the nose, you don't take off the number, right? Because what you're doing is really taking off a significant figure. And for a lack of a better description, you're making your measurement pretty crappy when you do that, right? You're making a lot worse measurement than it should be. And that's a very common mistake that people make when they do measurements. They go, 1.4 is what it says. So you got to maintain that with the 0 to maintain the proper number of significant figures and the proper measurement that you should take. Any questions on that? Anything that is digital, you should always record all the numbers that are there, because that's probably why they're there. They're kind of significant. So you should record usually all those numbers. Question on how to properly take a measurement here. So as I mentioned before, again, it's custom to record all those certain numbers plus the first uncertain number, and that gives you your significant figures. Now, another important thing in terms of measurements is accuracy versus precision. So when we are accurate, what it tells us is how close the measurement is to the true value. When we are precise, what that tells us is how close our measurement is to other values, other measurement values. Accuracy we use to see kind of how good we did, how close we were to the right answer. Precision, a lot of times we look at how reproducible something is. So sometimes when you do an experiment, you do it multiple times and see if you get the same result multiple times, and it would be very reproducible and very precise. As the classic throwing darts example, which I think you might even have a picture of. Let's say I threw some darts at a very badly drawn dartboard, and I throw the darts and I hit over here, and sadly I missed the board altogether. Am I accurate? I am not accurate. Am I precise? I am not precise, because I got one here, and then way over there as well. So they're not really grouped together, all those things. So that would be something that is not accurate and not precise. Let's say I said double or nothing. Let me throw them again in a friendly game. And let me clean up my board as well. There we go. So I throw them again and I hit here, here, and here. Am I accurate? I'm not accurate, right? Go throwing darts just to hit the bullseye. Am I precise? I am. I'm precisely not accurate, right? I keep missing in the exact same spot, which means you probably don't want to be standing that side of the board in case I miss really badly. So that shows you that you can be very good at repeating something wrong, right? You do something wrong every time the same way, you get the same result. So you can't be very precise without being very accurate. I do a triple or nothing because, you know, that's how we roll here. We'll go triple or nothing, and my dartboard's getting smaller. I like to think it makes it harder every time I erase this lane. But I throw it here and here and here. Am I accurate? Am I precise? Yeah, and that's, you know, sort of the goal when you take measurements, right? You want to be accurate and precise. You want to be able to get sort of the right answer and be able to reproduce that experiment or whatever you're doing to get that same answer every single time. Any questions on the difference between those two? All right, so that's a much nicer drawn dartboard, but I think it lacks the free hand that I drew, I think. All right, let's take a look at some of these here. I hope it didn't move. So if we look at this, we have 2 and 3 centimeters. We have our big difference there of 1 centimeter. There should be 10 markings, I hope, between which means in this case, once again, each of the smallest markings should be 0.1 centimeters. So that should be 2.5, that should be 2.6, 2.7. So we are definitely looking at something with a 2.6, which gives us this guy, this guy, this guy, or this guy. Is 2.6 the right one? No, because we have the ability, right, to go really one more place to the right. So we should be looking for something with 2 decimal places that has 2.6. So that would be these two. And if we did our precision by dividing this by 2, it is going to give us our 0.05. So it looks like D there, right, would be our correct answer. That number would have how many significant figures? Would have 3 significant figures. Yeah. So what you could do to figure out sort of the precision of the instrument, which is what all this plus or minus kind of thing is you take the smallest markings that there are on that piece of equipment and you divide it by 2. And that gives you basically how far you can take the reading to in that case. So you can take it to 0.05, which means basically you can take it to the second decimal place to reading. It doesn't necessarily have to be 5 at the end, but you could take it to that reading. The smallest marking in this case is 0.1 centimeter, because the difference between the 2 and the 3, there's 10 markings, if you count all those little guys. And each of those markers are 1 centimeters. So if you counted from the circle right here, that would be 2.1 all the way over to 3. If you get to these marking. Other questions? All right, so we'll take a look at this one. Kind of the same setup, I think. So we got 9. We also need to go to a couple decimal places. So I am thinking this should be our just over 9, 9.02 with our same precision. Any questions on that there? We talked about reading a meniscus in a graduated cylinder. Again, you want to read from the bottom of the meniscus. And if we looked at this, this is very similar to the one we did. That's 30 and 40, and there's 10 markings between each one. So each one's 1 milliliter, which means if we took the 1 milliliter and divided it by 2, we could go to 0.5 milliliters, or the first decimal place to where we could take the reading. And that would be right about here. It should be about 35. So that would be 36 some change. So 36.8 milliliters is what we should end up with on that sort of reading. Or it doesn't have to be again 8. If you saw it as 36.7 or 36.5, that's all good. The important part would be obviously taking the reading to the proper digit right there. You shouldn't be so off like you went, it's like 36.0 or something like that, or 35.0 or something like that. But you know, you should be in the ballpark. Super zoom a bit. Now, when we use something like this particular instrument here, this is actually a Buret, and Burets actually increase volume as you go down. You fill it from the top, you drop it out the bottom, the liquid. So the liquid comes out the bottom here. So as you can see, that's 28. This is actually 29. This is actually 30. So it actually increases as you go down in this case. So when we look at this, the difference between here is still 1 milliliter. There's actually still 10 markings, which means each one would be 0.1 milliliter. And obviously, if we took our 0.1 milliliters and divided it by 2, that would get you your plus or minus 0.05 milliliters. Now, this would actually be here 28.5. And as we come down here, our meniscus is in this area there, which is right before 29. So they went to 28.85 milliliters. So when you use something like a Buret, which we'll use towards the middle of the class, you want to make sure you understand sort of how the scale is going. Most of them kind of go like what we've been looking at, but a Buret does increase as you go down. So it's very common people read it wrong when they look at something like this. It's very common somebody will say, this is 29 point something, kind of reading upwards, but because the volume comes out the bottom, it actually increases as you go down. Any questions on any of that stuff there? All right, we will lay it up here for lecture today.